Welcome back to Multigrid Methods. So we're still in chapter 9, talking about additive preconditioners based on the subspace decomposition approach. So the idea here is to create a matrix B, which can be, or matrix B or C, which can be used as a preconditioner. That is, we're going to be interested in something so that, well, first of all, we really want to solve an equation which looks like this, A U equals F. And generally, you should think that A comes from the discretization of some partial differential equation via the finite element or finite difference method. We want to multiply A by a new matrix called B or C. I think we'll use C in this section, such that the condition number of C times A is a lot smaller than the condition number of A. So this is the idea, where C is some sort of, C is kind of an iterator matrix which appears in a generalized general linear iterative scheme. So remember, general linear iterative schemes look like this. So it's this matrix that we're going to be interested in extracting. This guy here, the iterator matrix for this general linear iterative scheme. And the additive part means that C can be written as C1 plus C2 plus C3 up to CR. So again, we're interested in solving an equation which looks like this, but the condition number of A might be very large. So we're going to precondition it by multiplying by a preconditioner matrix C that somehow is related to or appears in a general linear iterative scheme like this, and it's additive. So why would this be useful? This is useful because what we can show in the end, if we do this construction in a smart way, is that the condition number of this new matrix that we're creating, CA, is a lot smaller than the condition number of A. In fact, it can turn out to be order 1. So we're going to use our theory to actually prove this. Now, why would that be useful to us? The reason it could be useful to us is because now if we solve this precondition system using conjugate gradient method or steepest descent method, it's going to converge very rapidly, as long as we use this matrix as our coefficient matrix rather than the original matrix. So let's get into it. So last time we were building these things called hierarchical bases and hierarchical decompositions. I want to remind you that this, for example, this is the case where, what are we looking at? Well, I guess I don't know exactly which value for L is. So it's just some WL. And the idea of WL is that it's a space of finite element functions where every other degree of freedom is basically canceled out. In particular, the degrees of freedom that we nullify are all of the degrees of freedom that appeared in the mesh at the level below. So these are all nodes. These are all nodes in the nodal set NL minus 1. And we're going to nullify those. We're not going to allow the function to have a degree of freedom there. We're going to set that function to be equal to 0 precisely. But now, for the nodes that were added when we go to level L, those are the new nodes, I guess you could call them. So this one, this one, this one, and this one. We're going to allow the functions to be degrees of freedom at those nodes, but we're going to nullify the degrees of freedom at the nodes that were in the previous mesh, the mesh at the course level, L minus 1. All right, so that's what these spaces WL are. So the WL spaces are subspaces of VL. Okay, so VL is where you have degrees of freedom at every point. So for example, a function in VL will have a value which is non-zero here, here, here at all these 7 points. Okay, WL, we're nullifying those points, but VL has degrees of freedom at those points. So that means that WL is in fact a vector subspace of VL. All right, now we can show that VL is equal to a direct sum of VL minus 1 plus WL. And the reason is because this contains the new information of stuff which is not zeroed out at these points. And this the vectors in this space or functions in this space have degrees of freedom precisely at those points. So we can show, and we're going to show, that VL can be written as such functions, functions which have degrees of freedom at the nodes in L minus 1 and degrees of freedom at the new nodes. If we continue this construction here, what we can show is that VL is equal to a direct sum of W0, W1, all the way up to WL. All right, so I'll show you how that works. This is the key piece though, so let's see if we can show how this works. I think it's obvious how this decomposition works, but let me show you some algebra that proves it beyond reasonable doubt. So recall that IL is this nodal interpolation operator, and it works like this. If we have a C0 function, then we can always push it into the mesh VL just by sampling the values at VL, as long as the function is globally continuous. This is what we called the Lagrange linear nodal interpolation operator. So it has the property that if I have a V in C0, globally continuous function on the whole, on the closure of omega, then the value of the Lagrange linear nodal interpolation operator of V at the nodal points NLI is exactly just the value of V at those nodal points. So the way we can write this is as follows. So IL V, so we could write it as VL, I guess, V or VL. B is fine. So this is equal to sum. How many degrees of freedom are in level L? NL. So it's I equals 1 to NL. V at the nodes, NLI, times the nodal basis function, and psi Li. So this gives us a new function that is in the space VL. That's how the nodal interpolation operator works. But notice if I put in, so this is a function, I haven't written it explicitly here, but I hope it's clear. This guy is actually a function of x, as is this guy here. This is the coefficient that I'm using in this expansion of this basis. So the function of x is here and the function of x is here. So if I put in the value, let's say NLJ for x and LJ, remember this is going to give us a Kronecker delta, delta Ji or Ij. And that means that if we put in that value, NLJ, out pops VNLJ. Okay, so that's essentially what I said here. And we're using the fact that if I evaluate this guy at the nodes, then I get the Kronecker delta symbol. Now, we can use this Lagrange nodal interpolation operator in a number of different ways. We're going to use it in a kind of a slightly different way. Suppose that VL is already in the space VL. It's an arbitrary finite element function on level L. And what we're going to write is, we're going to write this VL in using some trivial representation, which turns out to be quite useful for us. Let's think about adding and subtracting IL minus 1 VL. So this is, of course, straightforwardly equal because this and this cancel and just leaves VL. And so VL equals VL. That's obvious. Now, why is this an impressive or important decomposition? Well, this guy here is the Lagrange nodal interpolation operator into the finite element space VL minus 1. So it's taking something which was in VL and pushing it into the coarse space VL minus 1. Okay, so this part here is in VL minus 1. Look at the decomposition we're trying to get. We're trying to show that every VL can be written as something in VL minus 1 and something in WL. All right, now let's look at this guy here. What is this? Well, I claim that this difference here is a finite element function that lives in WL. So this one is clear, but I think this one maybe I have to do a little bit of work to show you it's true. VL minus IL minus 1 VL should be in WL. Is that true? Well, how do we know that it's in WL minus 1? All we have to do is show that if I evaluate this function, this is now, you can call it a difference function if you like, you can call it WL. But this function here is, it's a function, all we know so far is that it's in VL. We want to show it's in WL. So how do we do that? Well, the way we do it is to show that its values at the nodes of L minus 1, level L minus 1, all vanish. Its values at those nodes vanish. So that's what I'm aiming to do right now. I'm going to put in the nodes NL minus 1J. So these are the nodes at level L minus 1. So we're going to evaluate here and here. What do we get? Well, I claim that we get 0. Why is this true? Well, the value of these two functions match at these points because what I'm doing is I'm pushing this guy down using this interpolation operator. So this guy has to have the same values as this at these nodes because I'm pushing it into VL, or sorry, VL minus 1. So this guy, remember, IL minus 1 is taking VL functions and pushing them down into VL minus 1 functions. So now they only have degrees of freedom at those values. And moreover, the degrees of freedom were exactly equal to the function values of the original function, VL. So these guys have to match at those two, at those degrees of freedom and L minus 1. And so their difference has to be precisely equal to 0. So if you can't wrap your brain around that, maybe draw a picture and convince yourself of that. I won't dwell on it any longer. Now, so this means that this function, because it's 0 at all the nodes NL minus 1, has to be in WL. Now all I have to do, so that gives me exactly what I wanted to show, right? But now I want to show that this decomposition is unique. So, and this is kind of, I don't recall if when I use this sort of notation, I mean that unique decompositions always happen. I'm blanking on that. However, we are going to show as part of this decomposition that it is a unique decomposition into these vector spaces. So this is called the direct sum. All right, so what we're going to do is assume that we have two different breakdowns into of this VL into VL minus 1 plus WL, where VL minus 1 is in VL minus 1 and WL is in WL. And I put I on here because there's two decompositions, so I equals 1 and 2. Well, we know that if each one of these guys, I equals 1, I equals 2, equals VL, then the difference between these two functions has to be equal to 0, right? So you just write 1 on one side and 1 on the other side, VL minus 1, 1, plus WL minus WL1 equals VL minus 1, 2, plus WL2. Okay, so the difference, if I just take the difference of these two functions, I have to get 0. But now look at this. So I have this difference here, because VL minus 1 is a vector space, it has to be back in the space VL minus 1. So this difference lands back in VL minus 1. And this difference here is in WL. Okay, and I can call these two differences respectively VL minus 1 and W, or maybe I should have put a delta in front of them. Okay, but in any case, this guy is in VL minus 1, this is in capital WL. Now, so another way we could look at it is to say, well, okay, this guy here is, did I say this right? Yeah, that's okay. Notice that I'm calling minus WL this difference here, but that doesn't matter. So you can say VL minus 1 is equal to WL. That's another way of saying what we've just written here. But how is it possible for something in this space to be equal to something in this space? Well, it turns out that the only way that that's possible is if both of these guys are identically equal to 0. And that's because these have degrees of freedom which are not on the same points. These have the degrees of freedom at NL minus 1, and these have degrees of freedom at every point except NL minus 1. So the only way they can equal each other is if both functions are identically 0. And so doing this proves that these decompositions here have to be identical. In other words, this difference is 0, so these two things have to be equal to each other, and these two things have to be equal to each other. So that proves the identity that we wanted to show, number 9. Now, how do we show this guy? Well, that's easy to do, because if we start out with VL, we just proved that that's VL minus 1 direct sum WL minus 1. And now we also know that we have a similar decomposition for this guy, so we could write that in. That's equal to VL minus 2 direct sum WL minus 2 direct sum. Let's see, I did that wrong. That should be L. So that's WL minus 1 direct sum WL. So just continue on. Now replace this guy. And then the last thing that you need to know is that V0 and WL or W0 are exactly the same. That was by definition. So you can go all the way down to the basement and continue this process until you get all the way down to here using 9. So 10 follows from 9. All right, so this is going to be a useful decomposition for us to know that VL can be written as VL minus 1 plus WL. So this is the old information at the old nodes. And now when I add new nodes to refine to get my finer mesh, well, that's going to produce degrees of freedom that are going to be precisely captured by these functions that are in WL. Okay. All right, so let's define a basis, or let's define something that will show to be a basis for WL. So define BLW to be equal to these functions called phi Li, I equals 1 to ML, functions in WL that satisfy phi Li are equal to, well, phi Li evaluated at NLWJ is the Kronecker delta symbol delta Ij. For I and j all the way from 1 up to ML. Now, I haven't defined this nodal set yet, so let's do that now. Where this nodal set, NLJW, j equals 1 to ML, is precisely equal to all of the nodes that are in the fine level mesh, except those that were in the coarse level mesh. So here's how we're going to do that. So the picture is, let's do the case where NL equals 7 again. Okay, now to get the next level of refinement, I'm going to refine with these red marks. All right, so now all the points in NL minus 1, those are precisely these blue points, except for the boundary blue points. Let's actually color the boundary blue points or boundary points differently. We'll color those in black. Boundary grid points, I guess I should. All right, so there's the boundary grid points. The blue points are all the nodes in NL minus 1. So this guy, and that one, those are all the nodes in NL minus 1. Okay. So this is J equals what? 1, 2, and 3. Now the red nodes are all the nodes that have just been added. Actually, right. So the red nodes are all the ones that have just been added. But what about this set? What is that set? That's actually the union of those two sets. That's these 7 nodes, the red and the blue. That's that. Now, what happens when I subtract away these nodes, the nodes that were in the previous set? All I'm left with are these 4 red points. That's precisely equal to this nodal set here. ML is the number of red points. So in this case, let's see, we can call this NL. NL was equal to 7. That was the total number of points, 1, 2, 3, 4, 5, 6, 7. And what is ML? ML is going to be the number of points left over. And let me be really suggestive in my use of colors here. So ML is the number of points left over after I subtract out the nodal points from NL minus 1. So that's going to be 4 points. So that's precisely this number here. It's going to be less than this number here. And in fact, ML is always equal to NL minus NL minus 1, because these points are distinct from, well, they're not distinct from this points. I'm removing NL minus 1 points from these NL points, and I'm left with ML distinct points left over, precisely these red points. So this is very simple then. The basis elements are the ones where I'm looking at the nodal points from this set, and phi Li has to be equal to, when I evaluated those points, NLWJ, I get delta IJ. So what does this basis look like? Well, there's one. There's another. Nope, that is not one. And finally, there. Okay, so they have to be functions in WL. They have to be functions in WL. So this is phi L1, phi L2, phi L3, phi L4, right? Those are each functions in WL because they have zeros at these nodes. That's what it means to be in WL. And with respect to these nodal points in NLJW, these guys here, these 4 points, I have to be 1 at, for example, phi 1 has to be 1 at node 1 and zeros at all the 3 other nodes, these 3. Okay, so looks like that function satisfies that. And the second one satisfies that it's 1 at node 2 and it's 0 at nodes 1, 3, and 4, and so on. So it looks like this is the picture of my nodal basis for this space. And this is a nice rendering of exactly that. Okay, so we have 4 basis functions by 2, 1, 2, 2, 2, 3, 2, 4. Okay, for the case where I guess n2 is equal to 7 and 1 is equal to 3. So remember we said that m2 is equal to n2 minus n1, and that's precisely 4 in this case. Now, it's not hard to show that this BLW is a bona fide basis for WL. We called it the basis. Let's see, right? When we defined this thing. Actually, we didn't call it a basis. We just defined it. So it doesn't really have a name. Oh, but I missed it. I did miss an important point, which I just noticed and I want to emphasize, and that is this. The basis for level 0 is just taken to be exactly the basis for level 0 of V. Okay. All right. So this result says that that is actually a basis for WL. And I hope that that's clear. It shouldn't be too hard to put together a proof for that. I'm going to leave that as an exercise. Okay, so now suppose that WL is defined as before, then what we're going to do is gather up those functions in the following way. So we're going to make a definition HL is equal to the union J equals 0 up to L of the BJWs. So the functions that I just constructed for my W basis. If I union over all of those basis elements, okay, not just at level L, but all the way from level 0 up to level L, then that gives me this new object called HL. And it turns out this, amazingly, is a basis for VL. This is a basis for VL. So do I have a picture of that? Let me see if I do. Here we go. So we'll come back to the proof, but let me give you the proof by picture first. All right, so now the first thing should be clear is H0 and B0V are exactly the same. They both consist of just one element, which is just this function here, this hat function. Now, H1 is comprised of the basis at level 0 plus the basis for W, the union of the basis for W at level 1. So that's these three functions. Okay, so I get two narrow ones and one really wide function. So that gives me 1, 2, 3 degrees of freedom. Here's the basis, the standard Lagrange nodal basis for level 1 for the space VL. So this one we already know, we've already proven that this Lagrange nodal basis is a bona fide basis for that space V1. And it has 3 elements in it, 1, 2, 3 degrees of freedom. Well, the number of degrees of freedom here is correct. No problem there. But what we have to show is that these bases span the space and are linearly independent. And this one spans the space. We already know this one, it spans the space and is linearly independent. This one has 3 elements in it. So if we show that this guy spans V1 and is linearly independent in V1, then this basis has to be a basis which is just as good as this one, just different, right? Different information, but it's still a basis. Okay, now let's look at H2. What does that look like? It's the basis from level 0 plus these 2 guys that I just added, plus the basis for W2, which is going to be these 4 hat functions, which we talked about earlier. So now I have 1, 2, 3, 4, 5, 6, 7 functions. They're all of different shapes and sizes. That's okay. They also form a basis for B2 or for V2, as does this Lagrange nodal basis. This would be the standard one. This was the one that you've seen before, these 2 over here, and this is the brand new one. And I've color coded this so that you can see the different levels coming into play. So dark blue, it's maybe a little hard to see on the screen here, but this is dark blue. You can, when you're following along in your slides at home, you can see that this is dark blue. The next level is going to be black, and then the finest level is going to be cyan. All right. So now we want to prove that this actually is a basis. It's equivalent to this basis. How do we do that? All right. So the result follows again, if we can show that HL spans VL and HL is linearly independent, because that would show that it's a basis, and we already know that BL is a basis. So it's well, actually, we're not really asked to show that it's equivalent, but we know that it's equivalent to the old basis BLV, or at least it's an alternative basis. So all we're really asked to do is show that it's a bona fide basis for VL. So we have to show that this is linearly independent, and we have to show that it spans the space. Okay, so how do we do this? To show that it spans the space, we have to suppose that VL is arbitrary, and then we have to write a decomposition for this using the elements of the various spaces. Okay, so the way we're going to do this is we're going to show that if we start off with an arbitrary VL, we can immediately write this as a bunch of W functions where each W is from Wj. And the technology we're going to use to do this is the Lagrange nodal interpolation operator. So here's how here's the idea. We're going to do this in this sort of a telescoping sum way. We're going to write VL as being I0 VL, that's the basement level, and then I1 VL minus I0 VL plus I2 VL minus I1 VL. So notice that this is going to cancel with that. That's going to cancel with that. And we're going to cancellations all the way up the chain. This will cancel with one previously until I just have VL. So VL equals VL. This is clearly equal to each other. Okay. Now, what we can show by the same technique that we used in the previous proof is that each one of these guys is in WL. So this guy here, we're going to call W0, and that guy lives in W0, capital W0. How is that true? Well, that's true trivially because we're using a Lagrange nodal operator, which is pushing us all the way down to V0, but V0 actually, V0, but V0 and W0 are the same. Okay, so this guy is clearly in W0. V0 and W0 are the same. Now, Wj is the difference between Ij VL and Ij minus 1 VL. Now, this is precisely going to have the property that it's 0 at all the nodal points in NL minus 1. And so this has to be, or sorry, NJ minus 1, I should say, at all of the nodal points in NJ minus 1. So the way we show it is Wj, when I evaluate at NJ minus 1, I, that gives me 0 for all I. And it's, again, the trick is, again, the same that we used in a previous proof. So, again, all we have to do is show this and show that this guy is in capital WJ, which I didn't say, but in fact, this is part of the proof that we gave in the previous statement. It was a lemma. There exist these unique functions, and the way we can decompose these into unique functions is this way. So if we find that we have a decomposition like that, then we know it has to be unique because all decompositions of that style are unique. All right, and again, we argue that this difference is in Wj, this difference, or this function is W0, and so we're done. So that shows the spanning property, that we can take any VL in VL and we can write it as a span of functions from HL. Well, actually, it's not quite not quite there yet because we have to show that now these can be written in the basis elements. So let's do that next. Now, since each Wj is in Wj, capital Wj, there are unique coefficients Cj1 through Cjm in R such that each Wj can be written in the basis functions from Wj. In fact, so these are the functions. So let's do it like this. See if I can not screw up the BWJ is a collection of functions like that. K equals 1 to MJ. Okay, so that's where these guys are coming from. So each one of these guys can be written as basis functions from that space. That's great. Now we can replace each one of these by this expansion. Okay, as we've done here. And now we can see that these guys are, remember, these basis functions are only from, this particular one here is only from BJW. But now the fact that we're summing over all J from J equals 0 to L means that we're drawing all the basis elements from all of these BJWs at all levels. In other words, we're drawing from the union of those. What is the union of those? So we said that HL is the union of those guys. So J equals 0 to L, BJW. That gives us this space HL. So in fact, what we've just shown is that we're writing all of these guys in basis functions from this full collection of basis functions. So that shows the spanning space, or that shows the spanning nature. In particular, what we showed is that we can write VL as being inside the span. But we all already know that the functions in HL are individually, they're a bunch of basis functions, but each one of them is in VL. So the span of HL has to already be in VL. So that shows that the spans equal each other. Okay, spans are exactly equal. So that takes care of the one thing, okay? But now notice that the number of elements in HL is exactly equal to the number of elements in the original Lagrange nodal basis. Okay, so that is exactly NL. So now we've got a spanning set which has exactly the same number of basis or elements as a basis. So that means two things: that this has to be a basis, number one, and number two, it's a little theorem from linear algebra that you may or may not remember. So if I have the same number of elements as this and both sets span, of course this is a basis, then this has to be a basis as well, which means that not only is it a spanning set, but it's linearly independent as well. So I guess way I should have written this is that if I can show that it spans and the number of elements is exactly equal to the same as exactly equal to NL, then I'm done. So I could have written it that way. So rather than be confusing here, I didn't directly show that it's linearly independent. I showed that this is true and the number of elements in HL is exactly NL, which is trivial. All right, so that proves it. And again, the picture of this is these hierarchical bases are different than the original Lagrange nodal basis. This guy, well, this I guess it's a little easier to see what's going on here, or it's easier to say what's different. What's different is that yes, we are using some elements from this original Lagrange nodal basis, but we're using also elements from the previous basis or the basis down below. And so this guy involves three basis elements as it has to, since it's a bona fide basis for V1, but it contains different types of functions. So it's this wide base triangle is in there, as are these two narrow base. Whereas the Lagrange nodal basis, original one, has just these three narrow base triangles. All right, so let's continue on in chapter 9 with our second slide deck, 2 of 2. Additive preconditioners based on subspace decompositions. The big picture is, again, we're trying to solve this equation. We're going to use some sort of iterative method. Maybe we want to use conjugate gradient method. And so in conjugate gradient, there's this idea that if the condition number is pretty large, then conjugate gradient method won't converge very quickly. Now, what do we need to work with conjugate gradient method? Well, A should be symmetric positive definite. It is. But the problem is A may have a large condition number, and we want to multiply by a preconditioner. And instead of solving the original equation, we're going to solve the preconditioned equation. Now, this seems, at first time I saw this, it seemed really stupid to me. This is this seems completely useless that you would you're just multiplying by C. Why are you doing this? Well, it turns out it's not a stupid idea, because we can apply now our not Gauss, but our conjugate gradient method to a new stiffness matrix or a new coefficient matrix, CA. And then the question becomes, well, the only reason why you would want to do this is if the condition number of CA is not too bad. Now, that means we have to look at the maximum eigenvalue of this product matrix over the minimum eigenvalue. That's how we define this condition number. And what we want to ultimately prove is that that is order 1. Now, the reason why this might be a nice gain for us is because we already showed that this has a crummy condition number. It's like order h to the -2 power. All right, which means h is getting small, and h to the -2 is 1 over a small number, so that's a large number. So as h gets smaller and smaller, as you do more and more refinement, then this condition number gets worse and worse. So those of you who are doing computations where you take a very large value for the number of degrees of freedom, and you notice your solver starts to work poorly, well, it could be that the condition number being large is starting to dominate your computations. So we might want to do something different. So we're going to use the hierarchical basis preconditioner to construct a preconditioner matrix C that makes this nice, that makes this order 1 condition number appear. If we can do that, then all of this will be worthwhile. Now, why is the preconditioner related to something called the iterator? So we said we know what an iterator is. No, normally I would call the iterator B, but now we're changing to C because that's the notation we're using in this chapter. So why is this related to a preconditioner? So that's a good question. Well, this is let's see if I can give a good short answer. Well, first of all, let me remind you of 2 things. So first of all, this came in 2 flavors. C could be additive, or multiplicative. Well, in multigrid, we saw that the preconditioner is actually multiplicative. All right, now we want to construct something which is different, a new kind of an iterative scheme where the preconditioner or the iterator matrix is actually additive. And the reason why this is useful is based on a discussion we had previously. And that is that, well, if it's additive, the C matrix can be written like this. And we can do these processes associated to each one of these iterator matrix, sub-iterator matrices in parallel. So in other words, I can apply this C by breaking it up into its constitutive parts and doing it in parallel. Now, applying an iterator matrix to some vector is entirely equivalent to doing the following process. So this is another key fact of general linear iterative schemes. We can write that as, so we could write this as UK plus 1 is equal to some operator called the GLIS operator. And the inputs to that would be F and UK. Now, what happens if I put in U equals 0, okay, to this operator here? So I don't want to do it that way. Let's do it here. Let's move this over. What happens if I put in and we don't have to use F here. We can use, let's say, a G. What happens if I put G and the 0 vector into the GLIS? What do I ultimately get? Well, this will be 0. This will be 0. And the application of the GLIS is just going to be C times, this is now G, C times G. So when you apply a preconditioner, really, it turns out the application of a preconditioner is only ever in the following sense. I'm only ever going to need to apply C times a vector, even though over here I said, whoa, it's C times A, C times a matrix. Actually, whenever you implement this in code, you're only ever going to have to apply it C to a vector. If you look at the preconditioned conjugate gradient algorithm that's detailed in the book, in the Purple Monster book, then you'll see that all I'm ever going to need is that matrix C times a vector. So the relationship between this as a preconditioner and this general linear iterative scheme is tied up in this statement here. If the general linear iterative scheme can be written, this guy here can be written as an operation, then if I put in 0 here and any arbitrary vector I want in this position, then the application of the general linear iterative scheme is the same as applying the iterator matrix or the preconditioner matrix C times a vector. So that's going to be an important point for the application of any preconditioner. And the fact that this is additive means that I can apply this preconditioner in parallel. Okay. And the reason is because this is ultimately going to be C1 times G plus C2 times G. Sorry. No, that's right. That is right. CR times G. Okay, so now each one of these steps can be done in parallel, completely in parallel. And you can throw them on a different processor. Processor 1, processor 2, processor R. And then finally you can combine them together. So this is why additive preconditioners, additive iterators can be so useful to us. Okay, so let me stop jabbering and get into this. So we need to connect the spaces WJ to VL in order to create our preconditioner. And this is going to be using the abstract framework that we developed in the first part of the first slide deck. Remember when we defined this that generic additive preconditioner. So now we're going to be making the connection there. Remember we had those Q matrices floating around there. And so now we're going to construct those Q matrices. So let BJW be as we constructed earlier. So that's the basis for each WJ, in fact. And suppose that we have BLV being the standard Lagrange nodal basis for VL. Okay, so these are our usual bases for Wj, and VL. Now, this is not a hierarchical basis. Remember, the hierarchical basis is when I union these guys together. For each j between 0 and L, there are unique numbers, and you have to be a little bit careful here. I give a warning. The number of indices in this section starts to really balloon, so we have to be a bit careful here. So for each j, there are unique numbers Q, J, L, K, I. Sorry about that. In the reals. For each K between 1 and NL, so there's K, it has NL indices, and I has MJ indices. That's that guy there. We're ultimately looking at level L as being the highest level, and level J, that's the intermediate level. So that's all four indices taken care of, such that phi Ji, so this is a basis element from BJW. Phi Ji, okay, can be expanded as K equals 1 to NL, QJKIL, psi LK, right? So what is this saying? What is this saying? Well, this is a basis element from this space, and this is the fine level basis function. Each one of these elements is going to be in the space VL. So we start out, that's how you would get the proof. So each guy, right, each phi Ji, we start out by assuming that's in Wj, but Wj is a subspace of VL. Okay, eventually, well, this space contains all of the spaces below it, like that. So if I have a basis element from a basis in that space, it's ultimately in this space VL. So of course, that means that there have to be numbers so that I can write this as, what is this? This is just a linear combination. So this is trivial, right? If I know this is in that space, then there's always a linear combination of elements of the, there's always a linear combination of involving the basis from that fine level space. And that's it. Okay, so that's the proof in a line, as long as you believe that this is true. Okay, that's the key revelation to getting that. Otherwise, that's a triviality, because it's just, yeah, of course you can write any function in a basis representation. Now this gives us these elements of these Q matrices that we're going to construct. But let's be really careful, because now I'm going to invert some indices like I guess like an idiot, I guess. But well, we'll see. Okay, so we're going to define the Q matrix QLJ. So this Q matrix is linking. So the way you should write this is as QJL is going to link WJ and VL. Okay, it's going to link WJ and VL. All right, so it's going to be defined as, remember, it's a matrix, as I just said. It's going to have NL rows, MJ columns. Now, which one is bigger? Well, NL is a lot bigger than MJ. NL is a lot bigger than MJ. So this is going to have many more rows than it is going to have columns. So let's just keep that in mind. Now, this is that matrix. And if I want to tell you what or how to define that matrix, all I have to do is to tell you what are the entries in each row and each column. Okay, each row and each column. And let's see here. I think that I think I actually made a mistake in that. Let's think about this. So if this is NL rows, MJ columns, then I should have how many elements? It should have NL elements. But here I'm saying it's MJ. So that these two numbers should be interchanged. It's a typo. K should come first and I should come second. Okay, so the L and the J means I'm linking WJ and VL. So those stay fixed. Okay, staying fixed. But now this first index should be from this space. So the K should come first and the I should come second. Okay. And so I think this is actually correct, but this just needs to be interchanged. Let's go back and make sure that those numbers jibe with what I had previously. So this number K, the middle number here, should have NL possibilities or come from this set, and this last one should have fewer. So K, yeah, I, fewer, okay? So this is okay, no problem there. I just need to interchange these two to get my sizing correct, because these matrices have to be always tall and skinny. Many more rows than there are columns. K should be the first index, I should be the second index. So, okay. Yeah, as I was going over that in preparation for the class, I realized that this inversion happened, but I thought I was correct. But now I realize it's actually incorrect, and so now I realize there is no inversion. It's this is the correct ordering. I should have preserved the correct ordering there. Okay, so suppose that QJL is a hierarchical projection matrix that we just defined, and WJ is a coordinate vector of the function WJ in capital WJ with respect to this basis here. Okay, so this guy is from a pretty small space, MJ. All right. Then the rank of QJL is exactly MJ. So that says it's full rank. So that's the number of columns. That's the smaller number. Full rank is the large is if the rank is equal to the smallest dimension of this, and the smallest dimension, of course, is the number of columns. So if it's full rank, then it has to have rank MJ. So that's what this lemma states is true, that the rank is exactly MJ, and if so, we want the coordinate. We know that WJ is the coordinate vector with respect to this basis for WJ. If now, instead of that, we want the coordinate vector with respect to the basis BLV, then that is exactly equal to taking this matrix and multiplying it times that coordinate vector. And that's going to give me now a coordinate vector that has NL coordinates. And that's precisely the coordinate vector with respect to the fine level basis BLV. So this is also an exercise, but it's not too difficult. And the way this works is, well, we know that WJ, right? WJ, since it's in here, I'll give you the proof right now. Since WJ is in capital WJ, then there exists numbers. Let's call them C, J, and how many of them are there? I want to use CJI. I equals 1 to MJ, such that, in fact, they're unique. This is my symbol for unique. E-bang. Exists unique elements such that WJ is equal to the sum I equals 1 to MJ CJI times the basis elements phi JI. Okay. So these basis elements here. Now, I also know that there are a bunch of basis elements, right? Or these basis elements, each can be written as a linear combination of these vectors. So now I'm going to throw this guy in there. So that means that I have sum j equals 1 to mj. And I think I did the sum k equals 1 to nl for that. C, let's see, I'll put that. Let me move this. CJI. And now each one of these guys has a sum, right? And that was what we called Q. That looks like a G. Q, J, L. Which was it? K, I. Times psi, K. No, psi, LK. Okay. And that comes from this expansion here. So I'm just dumping that in there. JKI, psi LK, JKI, psi LK. All right. Now, but that's now all I have to do is realize that this product here, I guess I should have used W for that. But in any case, this product here is precisely what we're looking for. I rearrange things, and that's precisely going to be this product. And once I have that product, no, sorry, it's going to be this part here. That's going to be the product I want. So once I get that product together, then that's precisely that, okay, or the entries of that vector there. And since that is multiplying these guys, that gives me the basis vector or the coordinate vector for this guy, but now in this basis. So it's not a hard proof, it's just a couple of substitutions. Okay, so the family of spaces WJ, we call these components of the hierarchical space, but they're not nested. So previously we had the nesting structure V0, V1, V2, okay? Those were all nested. However, these guys are not nested anymore. So just keep that in mind. Now, in chapter 8, we also had these prolongation matrices that could be stacked together. You could put, if you could stack them together in this sort of way. These ones cannot be stacked together anymore. So just keep that in mind. There's no stacking of these prolongation matrices. They're always connecting. They're always linking a coarse W space to the fine level VL space. They're always going from sort of all the way down from J all the way up to L. So they can't, it turns out that implies that they can't be stacked on top of each other. You can't multiply them. All right, so now in defining this preconditioner operator, I guess I lied. Maybe we're going to call this B. Let me see. Yeah. Okay. So I forgot that. So whenever you multiply the preconditioner, you're either going to call it C or B. Those are the two main things. And I was thinking I was calling it C, and I was earlier on whenever we were doing this in the fully abstract setting, but now we're going to switch back to calling it B. So I apologize. I should have made myself aware of that fact. Okay. So now we need to define these operators called B operators. All right, now these are going to be, unfortunately, I kind of have to work at the abstract level first, and then I'm going to bring this to the to the matrix level momentarily. So we're going to work at abstract level first, and then we're going to work at the matrix level after we figure out what these guys look like. Okay, so here's the way this operator works. If I take a function from wj, what I can do is I can turn that into a kind of what's the best way? I can turn it into what's called a functional, in fact, a linear functional for all of the functions in wj. And so this is the notation we use for the space of linear functionals on wj. So that's kind of a common notation. I should probably remind us of that fact. So wj, that's the space of linear functionals on wj. What is a linear functional on wj? A linear functional is something that if you give me two functions from wj, let's call it v and w, I can add them together inside of this operator f, which is linear, and the result is f of v plus beta f of w for all w and v that are in the space vj or wj, and any scalar beta. So this is what it means to be a linear functional. So that's the sort of object that I'm going to create. So once you give me a function, once you give me a function from wj, I can create a functional that's going to act on arbitrary elements of wj. And here's how it's going to work. I'm going to think of creating the functional from this number or this function here, wj. Okay, the little wj. And this is going to create a functional which is going to act on any other vj. Okay, so basically, given wj, I'm going to create a functional which can act on anything else. And the anything else I'm going to call vj and wj. And here's how it's going to work. I'm just going to add up sum r equals 1 to mj, wj, njwr, vj, njwr. Now, what are these? These are the nodes. This is the nodal set for w. And remember how we got the nodal set for w. The nodal set for w let's call it script L. Nodal set for w at level j, that's equal to the nodal set of v actually I don't think we wrote v there, but that's what it is, minus the nodal set at j minus 1. And you can put v's here if you want. That's the standard finite element space. So that's how we define these objects in that nodal space. Okay, we called those n, j, w, r, r equals 1 to mj. Lots and lots of subscripts and superscripts now. Okay, these were obtained by taking all the nodes at level j and subtracting out the nodes from level j minus 1, the coarse mesh. So this is how I'm defining this object bj. Very simple, but also very enigmatic. Why is it important? What is it doing for us? What's the use of it? So that's what we aim to show. Now, I don't like working with operators. And this course is called Multigrid Methods, a mostly matrix-based approach. And my point of view is that, working with these abstract objects can be kind of hard to deal with, but understanding what is a matrix or what's the underlying matrix for this linear operator is always, or generally always, easier to deal with and work with. Okay, so let's define a matrix, and from that, and we'll see that it has nice properties and essentially represents this this operation bj. So how we're going to do that? How are we going to do that? Here's how. So let's let bjw be the usual basis for wj. Remember, we called it phi j, and there were I equals 1 to mj of those guys in that basis. We're going to define the matrix bj to be a square matrix having mj rows and mj columns. And the way I can define the entries of this guy is to simply tell you how I'm going to, or how I can define this matrix is to simply tell you how I'm going to compute the entries of the matrix. So bj, this is the matrix, and these are the entries of it. Ith row, kth column. Well, that's going to be given to us by using this operator up here and putting in, for the first entry, instead of wj, we're going to put phi ji. And in the second entry, we're going to put phi jk. And of course, the way we define these two things is, of course, the sum over these valuations of these things at the nodal points. So that means nothing more than summing over what amounts to be Kronecker delta symbols. That's because when we put in these guys here and here, we're going to evaluate at these nodal points, but then we're going to keep in mind, well, this the evaluation of this guy at this nodal point is just going to be the Kronecker delta symbol delta IR. And what about this guy? This one is going to be the Kronecker delta symbol delta KR. All right, so I'm not sure. I guess I could put them the same, but the Kronecker delta symbol is symmetric about its coordinates, so that doesn't matter. Well, if I sum these guys up, then what I get is the Kronecker delta IK. Okay, so this is just equal to the identity matrix of size MJ. So in other words, this is just the MJ sized identity matrix. Now, why is this useful? Well, we're going to get to that next time when we start. We're going to use this B to define this hierarchical basis preconditioner for solving the finite element problem that we spoke of earlier. So in that case, we're going to write the stiffness matrix that we want to solve. It's going to be involved in this problem here, AL equals FL for some finest level of the finite element space. So those matrices that we just defined are going to be involved right here with constructing this preconditioner matrix, or this additive preconditioner, which now is going to be interpreted as a hierarchical basis preconditioner for this matrix AL, the original coefficient matrix. So we'll want to see, well, why is this thing useful to us? Is it why is it convenient? Does it help? Does it really, when I multiply this thing BH times AL, do I get a condition number now that which is small and reasonable to deal with? And the answer is going to be, turns out, actually, yes, we're going to be able to show that the condition number for this is quite small. So that's going to be the work that we're going to be trying to show in the rest of this section. And then time allowing, we're going to talk about another preconditioner, which is based on hierarchical basis called the BPX preconditioner. And so hierarchical basis preconditioner, BPX preconditioner, that's where we're going. So I'll stop there and I'll take any questions you guys have.